Each substance has characteristic properties. These properties can be classified into two categories: physical properties and chemical properties. Physical properties can be observed or measured without changing the composition of matter. Physical properties are used to observe and describe matter. Physical properties include color, odor, appearance, temperature, etc. Melting point and boiling point are physical properties of matter. For example, melting point and boiling point of water. Solubility is also a physical property. The measurement or observation of chemical properties requires a chemical change to occur. Charcoal or burning of matches shows their chemical properties. The International System of Units, SI.
The measurement of any physical quantity consists of two parts, a number and a unit. For a particular quantity, many different units may be used.
For example, the speed v of a car may be expressed in the form v equals 25 meter per second equals 90 kilometers per hour, where meter per second and kilometer per hour are alternative units for expressing the same value of the quantity speed. But the existence of alternative units can create problems. As an analogy, if you are traveling in a foreign country, the local shopkeeper might not accept rupees as they use a different currency unit. However, in many countries of Europe, they use a single centralized currency, the euro. You can use the same currency unit, the euro, wherever you go in the countries that have accepted euro as the currency. Similarly, a scientist in one country might need to read a research paper by a scientist in another country. It might be difficult for him to understand the paper if some very different units have been used for scientific measurements in that paper. To solve these problems, a system of units should be universally agreed upon to avoid confusion between scientists throughout the world. However, the units should be chosen so that they are readily available to all, are constant throughout time and space.
In 1960, an international agreement was reached specifying a particular choice of metric units for use in scientific measurement. These preferred units are called SI units, after the French Le Système International d'Unité.
The SI system has 7 base units from which all other units are derived. These 7 base units are for mass, length, time, temperature, amount of substance, electric current, and luminous intensity. The table here lists these base units and their symbols. In this chapter, we will consider the base units for length, mass, and temperature. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Prefixes are used to indicate decimal fractions or multiples of various units. This table presents the prefixes commonly encountered in chemistry. Let us now consider the quantities which are used widely in chemistry. First is length. Unit of length is meter, and its definition is given as follows. The meter is the length of the path traveled by light and vacuum during a time interval of 1 by 299,792,458 of a second. Second is mass. Unit of mass is kilogram, and its definition is given as follows. Mass is a measurement of the amount of material in an object. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. Third quantity is time. Unit of time is second. The second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the Ca-133 atom. Fourth quantity is electric current. Unit of electric current is ampere. The ampere is that constant current which, if maintained in 2 straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 × 10⁻⁷ Newton per meter of length. Fifth quantity is thermodynamic temperature. Unit of thermodynamic temperature, Kelvin. The Kelvin, unit of thermodynamic temperature, is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. Sixth quantity is amount of substance. Unit of amount of substance is mole. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. Its symbol is mole. When the mole is used, the elementary entities must be specified and may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. Seventh quantity is luminous intensity. Unit of luminous intensity is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 by 1012 Hz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian. Now we will understand some of these units in detail. Mass and weight. Do you know the difference between mass and weight? Mass is a measure of the amount of matter present in a substance. Look at these two cubes. Which of them has more matter, the bigger one or the smaller one? Let us find out. As we already know, scientists have decided the mass of a platinum iridium alloy kept in Sèvres, France, to be a standard 1 kilogram. This is used as a reference to measure all other masses. Using a beam balance, we see that 5 prototypes are used to balance the bigger block, hence its mass is 5 kilograms, while 10 prototypes are used to balance the smaller block, so its mass is 10 kilograms. So in this case, it is actually the smaller block that has more mass. Now, weight is the amount of gravitational force pulling a body. If the mass of a body on Earth is 10 kilograms, then its weight is nearly 100 Newton. Let us take the same body to the Moon. The Moon is smaller than the Earth and its gravity is only 1/6 that of the Earth. So on the Moon, its weight becomes only 16 newtons. During this journey, the amount of matter in the cube has not changed, but its weight changed. In laboratories, we use an analytical balance as shown. The SI unit is kilogram, but grams is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. Now, let us study volume. Volume is the amount of space occupied by an object. The SI unit of volume is cubic meter. However, this quantity is too large to be practical for the laboratory, so smaller volumes are used. Hence, volume is often denoted in centimeter cube or cubic decimeter units. A common unit, liter, L, which is not an SI unit, is used for measurement of volume of liquids. 1 liter equals 1000 ml, 1000 centimeter cube equals 1 decimeter cube. In the laboratory, volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. Now, let us define density. Density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass by SI unit of volume, which has a unit of kilogram per meter cube. This unit is quite large, and a chemist often expresses density in grams per centimeter cube, where mass is expressed in grams and volume is expressed in centimeters cube. Now, let us study temperature. It is summer. You are feeling hot. You exclaim, "Oh, how hot it is!" But how will you tell someone exactly how hot it is? You want to bake a cake. You know that you have to heat the batter. But how will you know how much to heat? To measure heat, to give a value to it, we use temperature scales. There are 3 common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here, K is the SI unit. The thermometers based on these scales are shown here. We sense temperature as a measure of the hotness or coldness of an object. We can understand the temperature scale by comparing with various references. The Celsius scale is based on the assignment of 0 degrees Celsius to the freezing point of water and 100 degrees Celsius to its boiling point at sea level. The Kelvin scale is the SI temperature scale, and the SI unit of temperature is the Kelvin. Historically, the Kelvin scale is based on the properties of gases. 0 on this scale is the lowest attainable temperature, minus 273.15 degrees Celsius, a temperature referred to as absolute zero. The Kelvin and Celsius scales are related as follows. Kelvin is equal to degree Celsius plus 273.15. The Fahrenheit and Celsius scales are related as follows. Degree Celsius is equal to 5 by 9 into degree Fahrenheit minus 32, or degree Fahrenheit is equal to 9 by 5 degrees Celsius plus 32.